Hi, I am Raghavan, Chemistry Faculty from ALPHORES College. I welcome you all for ALPHORES Chemistry learning classes. So today's session is 28th. See, in the last session we completed quantum numbers, okay, and we explained with different examples also. Now in this session 28th, we have Schrödinger wave equation. Schrödinger wave equation. See, according to Bohr's theory, we understood. So we can identify the position of the electron at any moment and the velocity of the electron at any moment. But after Bohr's theory, next we had de Broglie's concept. That is, de Broglie's concept explains that any moving object, that is any moving particle, possesses dual nature. That is both particle nature as well as wave nature. And according to de Broglie theory, electron behaves like a wave, not a particle. Okay, that means it shows wave nature. And then later, after that de Broglie's theory, next we have Heisenberg's uncertainty principle. So Heisenberg's principle states that it is impossible to determine simultaneously and accurately the change in position and change in velocity of electron revolving around the nucleus in the three-dimensional plane. So based on this de Broglie theory and Heisenberg uncertainty principle, remember, based on de Broglie and Heisenberg uncertainty principle, now the new vision leads to identify the maximum probability of finding electron around the nucleus. Okay, that is a new point we have to observe. Based on de Broglie theory and Heisenberg uncertainty principle, Erwin Schrödinger is explaining the maximum probability of finding electron around the nucleus in the three-dimensional space. Okay, that is Erwin Schrödinger wave equation can be read like this. The equation can be read like this. Okay, so this symbol is called dou. Okay, that is called dou. Next, another symbol is there. Okay, this symbol is called psi, but exactly it is represented as psi. Okay, p is the silent. So psi, dou and psi. Yes, the equation can be read like this: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square E minus V psi is equals to 0. Okay, once again let us read the equation: dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square E minus V psi is equals to 0. Okay, so this is the Schrödinger wave equation. So in this Schrödinger wave equation, this is Schrödinger wave equation. In this equation, let us write the terms. Okay, where psi represents wave function or amplitude of the wave. What is that? Psi represents wave function or amplitude of the wave. Okay, m represents mass of electron, and h represents Planck's constant. H represents Planck's constant. H represents Planck's constant. Okay, then Planck's constant. Then E is equals to, E represents total energy of electron, and V represents potential energy of electron, okay, and the difference between total energy and potential energy, it speaks about kinetic energy of the electron. Remember that E minus V, that means it represents kinetic energy of electron. Okay, the difference between these two is indicating kinetic energy of the electron. So these are the terms of Schrödinger wave equation. There is a term, another term is there, that is dou. Okay, we have to explain what is a dou and why it is, what is the significance. Okay. Let us understand delta represents what? The delta, this represents change. Okay. What is a change? Difference. For example, the concentration of a solution is reduced from, that is, say for example 1 molar to, it is initially we have 1 molar solution. After some time, after dilution, so the concentration of the solution is decreased from 1 molar solutions to 0.5 molar solution. Okay, that means delta, that means change in concentration is equals to, that is 1 minus, that is how much it is decreased, the final concentration minus initial concentration, that means decreased, minus. Okay, 0.5 m minus 1, so that is equals to minus 0.5 molar. How much it is decreased? 0.5 molar is decreased. Okay, that is called a change we can represent. Okay, that is only the point I wanted to tell. So what delta symbol represents? What? Change. It represents change. That means if the change is huge, big quantity, then that is identified by delta symbol. We know that. Okay, the delta symbol implies change. Okay, right. If the change is big, huge quantity, that is given by the symbol delta. Yes. Sir, what is dou? Let us understand. See, atoms are invisible microscopic particle. It is invisible microscopic particle. In that invisible microscopic particle, you are imagining that nucleus is present at the center. Okay, in that small, that is in that infinite small microscopic particle, you are imagining that the nucleus is present at the center of that atom. Got? Now around the nucleus, the electron still is the smallest particle. Still it is smallest particle. Okay, now in that smallest particle of atom, around the smallest nucleus, electron is revolving. Okay, that means it is related to only the maximum imaginary point of view only. Okay, we cannot get a photograph of that electron. Okay, so that electron, to identify that electron, I want to take the photograph of that electron. So what I have to do? I have to use a high resolution cameras, and to identify a particular object. So I have to use high frequency photon light to identify that electron. So what frequency photon light I have to use? High frequency, that is the frequency of the light must be greater than the diameter of the particle. Then only that particle can be identified or visible. Okay, that means, so when I use high photon light to identify that electron, so that electron absorbs photon energy from the light and changes its position instantaneously. That is why Heisenberg uncertainty principle states that change in position and change in velocity cannot be determined simultaneously and accurately, he said. Okay, that means, so that how much distance it can move, that is infinite small change, because atom itself is the smallest microscopic particle. In that smallest microscopic particle, you are imagining that the electron is the much more smallest. So by absorbing photon light, which you focus to identify that electron, so that by capturing some photon energy, the electron changes its position. Okay, that means there the change in position is very small, that you are describing as infinite small change. You got it? How you are describing that change? Infinite small change. The electron by capturing certain photon, so the electron changes its position, changes its velocity. How much change? Infinite small change. That infinite small change is given by the symbol dou. Okay, that is, the change is mentioned as infinite small change. That is denoted by the symbol dou. Yes. Now that is Schrödinger wave equation. So the complete name of that scientist is Schrödinger wave equation. It describes the probability of finding electron around the nucleus. Yes. So Schrödinger wave equation is based on, he describes the probability of finding electron based on de Broglie theory and Heisenberg uncertainty principle. Okay. Then this equation can be represented like this. So okay, that is V bar square psi plus this part, complete this part, that is okay, that is V bar square psi plus 8 pi square m by h square into kinetic energy, that is E minus V psi is equals to 0. Yes. This equation can be represented, that is h angle psi is equals to E psi. Okay, that is, this equation can be represented like this, where in this equation we noticed one new term, that is called V bar square. This V bar square is called Laplacian operator. That is, in the calculation or in the derivation of the quantum mechanics certain equations, so there are certain mathematical operators are used, that is, here it is called V bar square is called Laplacian operator. Okay, Laplacian operator, and this equation is mentioned like this, that is h psi is equals to E psi, where h is represented like this. The h is represented given like this. H is given like this, that is h is equals to V minus h square by 8 pi square m into, that is dou square by dou x square plus dou square by dou y square plus, it is dou y square, okay, dou y square plus dou square by dou z square. Okay, that means psi. So the psi factor is given like this. So that is h psi. Okay, h psi. This is h psi is taken that as a common. So this is the, where h angle is equals, it represents Hamiltonian operator. Remember, the second operator in the Schrödinger wave equation is called Hamiltonian operator. The first operator is called Laplacian operator. Okay, right. The Schrödinger wave equation, the complete Schrödinger wave equation can be represented like this. Okay, now where psi represents what? Psi represents r, theta, eta. Okay, that psi, see, this r is, see, in some books it is mentioned as that capital R is equals to, it is nothing but your psi. Okay, the capital R that represents psi only. Okay, it is not a different one. Okay, right. Now psi is equals to R. Okay, that means this R depends upon, that means radial axis. So what is that radial axis? Around the nucleus we can assume that x-axis, or you can assume y-axis, or you can assume that is x-axis, y-axis, or you can assume z-axis. Okay, now this psi value depends upon principal quantum number and azimuthal quantum number. Okay, the psi depends upon, the value depends upon principal quantum number and azimuthal quantum number. So this is also called, this is radial function, we can say. Psi is nothing but your radial function, we can say. This radial function can be, it depends on principal quantum number and azimuthal quantum number. Be careful, it is radial function. Okay, this is azimuthal function. Okay, this azimuthal function, next one, azimuthal function is called, that is theta. The theta depends upon, it depends upon azimuthal quantum number and magnetic quantum number. Okay, the theta function, that is azimuthal function, depends upon L and M, that means azimuthal quantum number and magnetic quantum number. Next, this is called orientation function. Okay, this orientation function, so it depends upon, this function depends only upon magnetic quantum number. That is one important point. Okay, once again let us see. So this psi means R, that is radial function. The radial function depends on principal quantum number and azimuthal quantum number. Okay, got it? Next, the azimuthal function, where is that? Theta function. azimuthal function. This azimuthal theta function depends on azimuthal quantum number and magnetic quantum number, L and M, right? Next one, orientation function. The orientation function, that is eta function, orientation function depends only on magnetic quantum number. Depends only on magnetic quantum number. Now, we understand from this discussion, we concluded one point, that is the quantum number which is not derived from Schrödinger wave equation, which was not explained by Schrödinger wave equation, that is nothing but spin quantum number. We have principal quantum number, azimuthal quantum number and magnetic quantum numbers, but not spin quantum number. That is another important objective question. Which among the following quantum number is not obtained from or not derived from or not explained by Schrödinger wave equation? That is nothing but spin quantum number. Okay, remember that point is important, right? Next, the above equation, this above equation can be given like this, can be represented like this. Psi is equals to RNL, that is radial function, and this is the sum of these two, that is theta function, that is angular momentum, that is azimuthal function and orientation functions together, it is represented like this. Okay, the equation I represented like this. The above equation can be represented like this. Psi is equals to R, yes, and this sum of these two, the product of these two, or you can say that is azimuthal function and orientation functions are represented. That is because both of depends on only L and M, whereas this depends N and L. Okay, this A represents angular wave function. That A represents angular wave function. That angular wave function implies the meaning of, that is azimuthal as well as orientation. That is called angular wave function. Okay, the equation, the above equation can be represented like this. Okay, now after this, next we have, what is that psi? Psi or capital R, that is called radial function, or it is called wave function. Radial function or wave function. What is that radial function or wave function? Yes, okay. So up to this we have some information. Now still we have to discuss. Okay, what is that A? A represents angular wave function. Okay, now I am removing because I need this space for writing. Okay, yes. Now let us describe what is psi. Now let us see important concept, significance of psi. Significance of psi. Significance of psi. What is that psi significance? Let us see this. Above the plane, the psi is positive. Below the plane, the psi is negative. Along the plane, psi is equals to 0. Yes. Along the plane, psi is equals to 0. So what does psi represents? Psi represents, already we mentioned that is nothing but amplitude of the wave. Yes, that means height of a crust or depth of a trough. Height of a crust or depth of a trough, that is called psi, isn't it? Height of a crust or depth of a trough, that is nothing but psi. Okay, still it is in doubt. What is the exact significance of psi? Psi represents wave function or amplitude of the wave, or you can also call it as radial function. Okay, radial function. What is it, radial function? That is nothing but probability of finding electron around the nucleus in the radial axis. Okay, so what are the values of psi? So above the plane, psi is positive always, and below the plane, the psi is always negative. Along the plane, the psi is equals to 0. Okay. To explain the meaningful solution of psi, to explain the meaningful solutions of psi, that meaningful solutions of psi are called eigenvalues or eigenfunctions. To explain the meaningful solutions of psi, okay, we require certain quantities to explain the meaningful solution of psi. They are called eigenvalues or eigenfunctions. Okay, to explain them, psi must to obey the following boundary conditions. The boundary conditions of psi. Boundary conditions of psi. What are the boundary conditions of psi? Psi must be finite, not infinite. Psi must be finite. That means a definite value. Second, psi must have single digit value. And third, the maximum probability of finding electron from plus infinity to minus infinity. That is the highest probability of the finding electron from the nucleus plus infinity to minus infinity. Now these are the three boundary conditions. Since the psi could not satisfy the boundary conditions, once again I'll explain. Okay, to explain the meaningful solutions of psi, that meaningful solutions are called eigenvalues. I'll write here. What are that? EIGEN, eigenvalues or eigenfunctions. To explain the eigenvalues or eigenfunctions, psi must obey the following boundary conditions, like psi must be finite, psi must have a single digit value, and the maximum probability from plus infinity to minus infinity. Since psi could not satisfy these boundary conditions, therefore psi has no physical significance. Important point. What is the physical significance of psi? Okay, psi has no physical significance. No physical significance. Important point. Psi has no physical significance. Okay. It is concluded psi has no physical significance because it did not satisfy the boundary conditions. So therefore psi has no physical significance. Okay, then so psi has no physical significance. That means we could not explain the complete functions of the psi because psi has no physical significance. Now, according to the concept of light, that means according to the concept of light, the intensity of the light wave is directly proportional to the square of the amplitude. According to the concept of light, the intensity of the light wave is directly proportional to the square of the amplitude. Is amplitude we consider as psi. So in place of psi, now this is nothing but our amplitude only. The maximum displacement of the wave, light wave, is nothing but amplitude. Here in place of amplitude we are using the psi symbol. Okay, that is why in place of amplitude now we are using psi square. Okay, you got it. So now the next we are introducing psi square. What is that psi square? Yes, you got it clear? I repeat, according to the concept of light, the intensity of the light wave is directly proportional to the square of the amplitude. Therefore, in place of the psi, because psi is representing amplitude of the electron wave, so in place of amplitude, that is psi square is introduced. Okay, that is psi square represents the probability function. It represents probability. It represents probability function. What does it mean? Probability function. That means it explains or it represents the maximum probability of finding electron around the nucleus. Okay. So finally, what is the conclusion? That is psi and psi square what are the values of psi and psi square explains us. The values of psi and psi square both represents orbital. It explains, it describes the orbital. That is the significance of psi and psi square. Finally, we explained to this. Okay. And the next concept goes to orbital. What is an orbital? Orbital means the maximum probability of finding electron around the nucleus in three-dimensional space. Yes. So already we concluded that psi and psi square both are representing an orbital. Orbital means the maximum probability. What do you mean by maximum probability? What is the percentage of probability? Is it 50% or 40% or 70 or 90%? What is that? Yes, the 95% probability of finding electron. Remember, 95% probability of finding electron around the nucleus in three-dimensional plane, that is called orbital. Now once again, the description of the orbital. The 95% maximum probability of finding electron around the nucleus in three-dimensional space is called orbital. Okay. The next concept we are going to take up, orbital. Okay. That is psi square. That is orbital. To describe the orbital, see, there is a factor, that is around the nucleus we are describing the maximum probability of finding electron. Okay. So now let us remove this maximum probability of finding electron around the nucleus. So this one electron, this is the nucleus, around the nucleus, and in first photograph we can identify the position of one electron at this position. That is the point. When we take the photograph of that electron, we obtained as the spot that electron. That electron, by absorbing photon light, that electron can move, can change its position somewhere else. Okay. Then third photograph, the position of the electron may be here, maybe here. Okay. In the next photograph, maybe here. So now we are taking the photograph of one electron species, that is hydrogen atom only. Okay. Now after collecting large number of photographs, now you are observing what is the probability of that electron around the nucleus. That one electron could appear in these probable positions. That one electron can appear in these maximum probable positions around the nucleus. That one electron can appear in these maximum probable positions. Far away from the nucleus also probabilities appear, but close to the nucleus also probabilities appear, but maximum probability in this area. That is the radial distance. The radial distance where the probability of finding electron is maximum is called radial probability. That is called, next is we are going into the radial probability. Radial probability. Okay. Next we are going into this one, radial probability. Okay. Radial probability. Okay. See, psi and psi square, we explained that psi and psi square represents orbital. It represents an orbital. Now we are coming into the radial probability. What is that radial probability? So radial probability explains the maximum, that is the infinite small volume. See, around the nucleus, once again let us see the probability of finding electron we have, and far away from the nucleus also probability we can identify, but the probability where it is maximum, yes, in this distance around the nucleus the probability is maximum. This area is called, that is radial probability. What is that radial probability? The definition is the infinite small volume, the infinite small space, or you can say the infinite small volume around the nucleus where the probability of finding electron is maximum is called radial probability. Okay, this radial probability, or it is also called D function. This is mathematically represented as 4 pi r square dr psi square. Okay, the radial probability or D function is represented mathematically as like this. This is very important point. Okay, So the important points we mentioned, okay, clearly it is very, very important. That is radial probability we described. Okay, what is the radial probability? The infinite small volume around the nucleus where the probability of finding electron is maximum. That is called radial probability or D function, and it is mathematically represented like this. So we can draw graphs between radial probability versus radial distance. Okay, so that is called a radial probability distribution curves. The radial probability distribution curves will discuss simultaneously along with the shapes of the different orbitals, right?